Another question that came up was this fact that the W got fixed. And so we could ask the question, in general, when will that happen? So when will the W's that are showing up in our Wilson coefficients be fixed by external kinematics? And actually, that's going to happen in the following case. We can actually state when it will happen quite generally. So imagine that we had an effective theory SET that had multiple collinear directions. So then we could build operators out of all those different collinear fields, and we would do it with our building blocks, which are chi-n or curly bn for each n. And if our operator only involves one building block for each direction, then it's going to be the case that the value of those labels or those omegas are always going to be fixed by external kinematics. So let me just write down another example. Imagine we had something like an LHC process where we had two gluons coming in and two quarks going out. But we'll think about this as PDF, as sort of protons colliding, coming in from two different directions. Let's call them N2 and N3. And then going to two jets, transverse to the axis by a large amount. So they're also two different directions, which I can call N1 and N4. So this process of glue-glue goes to QQ bar, which is really PP goes to dijets. As long as those dijets are well separated from the beam axis, which is the case we're interested in, then we have this situation where we have four different ends. And so what kind of operator would you write down for that? Well, you'd have dW1, dW2, dW3, dW4. You'd have a Wilson coefficient that could depend on four different W's. And you'd then write down some operator out of building blocks, N1, W1. I'm not going to worry about all the indices, but I'll worry about some of them. That would look like that. So I just put down some operator that's got the right structure. It's got two quarks, two gluons. I make the gluons these B perps. I've chose to contract them. Each of them has a different direction. This is an N1. And each of them also gets a corresponding large momentum, and the Wilson coefficient can depend on those large momenta. Okay, so this would be the operator that would describe that process. But again, if you think about the renormalization, then if you think about the renormalization for a minute, the collinear diagrams aren't going to involve contractions between this guy and any of these other guys, because these guys are totally independent. They're a different Lagrangian. So the contractions are, again, just like the kind of calculation that we did. The collinear diagrams are just coming from this thing alone, and they don't care about that stuff. So it's actually the same calculation that we already did for beta S gamma. If I wanted to do the collinear diagrams here, and then I would have to do the collinear diagrams for each of these guys, but it's kind of independent. And again, the W1 is external to that calculation, so the anomalous dimension would be outside it. It wouldn't sort of appear and get throws into some loop integral momentum. And so if you think about what can fix these W's, it's really only external information. So what are the momentum fractions of the incoming quarks from the PDFs? What are the energies of the outgoing jets? That's the type of information that even in this case would fix the W's. So So if we were to calculate the Wilson coefficient for this operator and do its renormalization group, there would again it would again be of a product form. There's no convolution, just a product for this Wilson coefficient. OK, so when could that not be true? It could not be true if, for example, we had a chi-bar and a chi that were in the same direction. So if we're in a situation where all the objects are different directions, then that's what happens. And it's pretty simple. Let's also do an example. When is it not true? It's always good to have a counterexample. And it would not be true if we had an operator like this. So here's an operator with just two quark building block fields. I give them different labels because in general the Wilson coefficient could depend on their large momenta. But now they're in the same direction n. So they belong to the same collinear sector. And in this operator here, we would actually no longer be in the case where sort of this thing would totally decouple from the loop integrals. So if we think about inserting this operator, then some of these guys here will involve loop momenta. Actually, it turns out that one combination of the W's is still fixed by external kinematics. And so there's kind of an overall, think about the overall delta function on this product. That guy would be fixed, and then some difference of these W's would not be fixed. That's the true story, but at least one combination is going to involve the loop momenta. And what does that lead to? How does it complicate what we've already said? What that leads to is that when we formulate the anomalous dimension equations, they also involve integrals. So for this guy here, for the one momentum that's not fixed, so in general there's two, and this is the one that's not fixed, we would get an equation that looks like this. Rather than the simple product form, there'd be an integral on the right-hand side. And indeed, actually, if we do the renormalization of this operator that I wrote up there, just that simple quark operator, you actually reproduce a bunch of classical evolution equations. That are of this form. So even just the simplest possible case we can think of where things are not fixed gives us a bunch of interesting results. So for deep inelastic scattering, then what you're getting is the Altarelli-Parisi equation, or D-Glap equation. And the evolution of the operator would be the evolution of the parton distribution function. That's one thing that would be encoded in a renormalization of that equation. There's other processes that are actually, some of which we may talk about later on, that are also encoded in this same type of operator, kind of a different projection of it. And one of them leads to something called the Brodsky-Lepage equation. And then there's another one that's showing up in something called a process called deeply virtual Compton scattering. OK, so the one that's most familiar is the renormalization of the PDF. And you may remember that the renormalization of the PDF has this form of having an integral. That'll come out of renormalizing this operator. We'll do that case. OK, so in general, the kind of structure of the effective theory is leading us to kind of find out what the structure of the renormalization is. And you can reproduce some sort of well-known classic things, but it comes out actually pretty easy. OK, so I'm going to do this case. But I'm going to do this case in complete with all sort of the details filled in. So first, I have to convince you that in deep inelastic scattering, you actually get that operator. And we'll see precisely what kind of matrix elements of that operator show up in deep inelastic scattering, why we get that operator. And then once we're convinced that we have that operator, and we'll actually derive a factorization theorem that involves that operator, then we'll talk about its renormalization group evolution. And I'll show you that it has this form that I'm writing here.